Our next speaker is Pierros, Sierra Victor 1 Quebec Victor Echo, who is going to give us a talk on the Libre Space Foundation, who were winners of the Hackaday Prize in 2016, was it? 2014.
Yeah.
Thank you.
Thanks. Good afternoon. My name is Pierros, and I'm going to be talking a bit about Libre Space Foundations and some of the projects that we're working on or we have worked in the past. So a bit about the foundation itself. We were founded in 2014 after the Hackaday Prize was announced. And Libre Space Foundation is basically a non-profit foundation with global membership. And our goal is to design and build and deploy technologies, open source, software and hardware in space. So whatever technology we can open source or we can create from scratch, that's what we do, and everything is space focused, whether that's downstream technologies, midstream or upstream, actually sending things to space. It all started, at least for the first project, which is the SatNuke project. It all started in the hackerspace in Athens, just a local, typical hackerspace. You would expect like a bunch of tools and a bunch of hackers like coming together and creating open source projects. And many of us were space aficionados, like we just liked space. Most of us radio amateur operators, really keen into working Oscars back in the day. Not so much anymore. More focused on digital transmissions and the digital side of things now. We were just building our own antennas and trying to figure out how to optimize many of the things that we do on ground station operations. And that's how we came up with SatNuke as a project. SatNuke stands for, I know the name is not really easily pronounced, but it stands for Satellite Network Open Ground Station. So it was a mashup of basically the basic ideals behind the project. How many of you have heard SatNuke before? Okay, cool. We went on to create a project which initially, through the early beginnings of it, it was basically just for the first couple of days, literally, it was a concept of creating an open hardware ground station. Like we wanted to create the rotator itself, the antennas, the instrumentation, the RF side of things. And then we said, that if we can make it affordable enough and we can make it in a way that we can create community around it, then we can create a global network of such ground stations and actually use as much of people's hardware and stations as possible so they can track all different satellites that are out there. We went on to win the Hackaday Prize, and that was a big boost. On two different fronts. First off, monetary. It was actually almost 200K that we used in order to kickstart the foundation and continue investment in the projects, but also a huge community boost. It got us, well known on the projects that are neighboring that, specifically on the open source community, and gradually also in the radio amateur community through talks like this and our presence as global community members. The goal of SatNuke is pretty simple. I'm not going to go into all the details. We have had presentations yesterday and today about CubeSats and many different satellites coming up there, and I'm kind of preaching the choir here about why it is important to have as many observations as possible for the satellites that are out there. But the difference and the thing that sets us apart from typical ground station operations is the automation around it. We would like to automate pretty much everything, like the tracking itself, obviously, that's already done through software, manually, locally, but also the demodulation, the tuning, the Doppler shift, obviously, the data decoding and the uploading of all the artifacts that you can get from an observation back to the network. We've seen a surge of many different CubeSats, nanosatellites, or even larger satellites that are actually using radio amateur bands, and we can track and follow their payloads and transmissions over the past years, and the projections are, just blowing up in terms of what we're going to be doing in the future. So let's break it down a bit. What is SatNukes in terms of the actual hardware and the electronics around it. Well, the first thing that you might need, and most of you already have ground stations, so you kind of already know that, is that you need a rotator, unless you have an omnidirectional antenna and you're okay with only receiving, like really loud birds. Then you would need a rotator and directional antennas, right? And like for us, there are two different options. You can bring your own. Pretty much every rotator controller supported by ROD CTLD, that's a HamLib library, is supported on SatNukes, and we're talking about the vast majority of the market out there, even DIY rotators that other people have built. And then you can also build your own with open hardware designs that we have published. That's version 3 of the rotator, at least the internals of it. And you can notice here, you can see like 3D printed parts and commercially and off-the-shelf available materials like aluminum rods and things like that. There's two different options. There's a DC motor option and a stepper motor option. So really flexible in terms of the things that you have around if you want to, start building a ground station rotator yourself. And the rationale behind it was, well, not only to build it open hardware because we want to have a full open stack, but also bring down the price as much as possible. Like if you're familiar with rotator prices, we're talking about double or triple that, to start with the base models. So trying to keep that, as low as possible and as affordable for people to build was a key factor in getting us to create an open hardware version of it. Then regarding the rest of the things, like the electronics, like the RF instrumentation, and the computer that actually runs the ground station autonomously by itself, our reference platform right now is a Raspberry Pi with an RTL SDR, and that's because, well, again, trying to bring costs down and make it as affordable to people as possible, we thought that we should go with the most available solution and easily procured solution that it's out there. That's not to say that the setup that we have in terms of software or the guides that we have are not working with other SDRs. Pretty much every software-defined radio that's supported by Osmo SDR should be okay and work with it, and we actually do that. We have Ethos Research B200s, we have AirSpice on ground stations, we have what else is out there? HackRFs, FunCube doggles. So everything that is supported by GR Osmo SDR is tested or some way deployed in a ground station of SatNukes out there. Although there is a caveat there, which is high sample rates are not really working well with Raspberry Pi. So your SDR should be able to support good quality of a low sample rate, which is not necessarily available on all SDRs out there right now. So that's a consideration to keep in mind. And of course, if you don't like the Raspberry Pi and you like to switch to something more powerful or actually actual hardware, like a laptop or a workstation, you can do that as long as it runs a Linux platform with Python 2.7 and GNU Radio. Well, one of the latest GNU Radio. Like that's one of the struggles that we have right now, and trying to figure out a way to get as much support as possible on different Linux platforms, and GNU Radio versioning is not really helping out on that, but I think that we worked through it. And of course, a low noise amplifier is really recommended, depending on your antenna setup and what birds you like to follow. We have a couple of reference, ones that we used in the past, and we know they're working good. LLA for all is one of them, and there's all sorts of designs out there, so you can, buy or create your own low noise amplifier. This is some pictures of satellite ground stations on the SatNukes network right now. This one is in Athens, in the local hackerspace. This one is Corys on US. That's an omnidirectional VHF turnstile out from Australia. This is Alex's setup in Denmark. And that's a California setup with you see here the rotator, that's a portable rotator. I don't know if you've seen the project. It's like a really small portable rotator coming out from a California company. And they set up a SatNukes ground station so they can display how the rotator can be used, basically. And stress test it, because we put a lot of observations on those ground stations, mainly because it's automatic, so it's kind of like, easy to do. This is a map showing the complete list of different ground stations that we have. That's not all necessarily in production. So we have two different instances of the network. There's a production one and a development one. The production are ready ground stations that we know that they're working well and we can rely on them on different observations. And then we have the development ones which are under testing or under construction. So basically you have like people putting up a Raspberry Pi and probably not a stable setup, kind of like a temporary one, and trying things out with the software. And then once they're okay with it, then they move everything to production and they declare the ground station ready for automated observations. The count of them on production right now, we have 17, close to 20 if we're okay next week on a couple of ground stations. And then on development, it's like more than 40 around the world that are doing that right now. And we've seen a large spike of ground stations over the past couple of months, mainly because we made it much more easier in terms of the software for people to get started with. I'm going to come to that in a sec. Now, that was kind of like the local setup, right? Like the ground station, the rotator or not, the antennas, the SDR, the single board computer, and everything else that is local to you. And then when you go on the network side of things, we have two different things. There is db.satnux.org, and this is a crowdsourced satellite database. And this is kind of like a separate project that we spun out of SatNuke's network. Mainly because when we first started, like our only source of information around satellite frequencies back in the day, like 3 years ago, was various different blogs from people, like long-time contributors on this area, like Mike Rupert's blog and P0Sat blog and other blogs that are out there. And they have done a fantastic job on that, but it's really seems kind of like a duplication of effort, and we would like to involve as much the community around it as possible. So what we did is we created a website that basically holds the frequencies, the drifted frequencies, the advertised ones, information about the satellites themselves, the Keplerian elements, and everything else in one place through an accessible open API so that other applications can also tap into that. And of course, we use it on SatNuke's network, but we've seen also usage from other programs out there, like gpredict from Alex. The prediction software actually fetches frequencies from SatNuke's DB, and other Android applications that you might be using. Like there are 3 or 4 of them that are fetching the frequency information from db.satnux.org, and you might have not noticed that. The concept here is that we would like as many contributors as possible to the DB. So you don't have to have a station. You don't have to, really even be into observing satellites. But if you are a, let's say, database and archival information enthusiast, then you can join, db.satnux.org and start submitting, information and keep things updated in there. There is also a part of db.satnux.org which is storing the telemetry data itself, whether that has come from a SatNuke's network observation or if that was done through a manual observation by people. So I don't know how many of you are familiar with TLM Forwarder by Mike Rupert. That's an awesome piece of software that you can use it to locally decode many different frames from many different satellites. I think it's supporting almost like 40 satellites right now or something. And then once this is decoded locally and you can see the data and everything else, then that pushes this information back to db.satnux.org. Initially, there was a different server set up just for TLM Forwarder, but then we reached out to Mike and Jan, P0Sat, and we joined efforts. And now everything ends up in db.satnux.org, and it becomes readily available back to everyone through the RESTful API that we have on DB. Up to date, we have 216 satellites in there with frequency information, like over 350 transmitters. Some of them have multiple transmitters, obviously. We have approximately 200 contributors, like people that are actually going in, changing frequencies, submitting information, and everything else. And then over 5 million frames from 80 different stations that are submitting information back to db.satnux.org. So that's kind of like the not necessarily specific to SatNuke's network part of SatNuke. And that's why we created it as a separate website. So we didn't want to enforce to people that they have to have a SatNuke station built and connected into the SatNuke network in order to be able to be part of such an effort of archiving as much information as possible, payloads and information about satellites. And then when we go to the network.satnux.org, this is the base of operations for the network, basically. It's the central scheduling system for SatNux. You can schedule many different observations, manage and available and capable ground stations to actually do that. So there are all sorts of different scenarios that you can run through the network itself. For example, collect all telemetry data from a specific satellite from this time frame, and then the network responds with the available ground stations, and you can schedule those operations. So it goes like this, but you can go the other way around. You can say, I want to see all the predictions for passes for a specific station, and then start scheduling specific satellites that you'd like if you are the station operator. So there's really many different sorts of ways you can go about it. But the end result is basically this, like the scheduling that is happening on network is then fetched locally from the client itself, and the observation happens, and then all the artifacts are uploaded back to the network. Once it's finished, each observation, then it uploads back minimum 2 types of thing, and that would be the waterfall itself. So you can have a visual representation of what happened during the observation on a span, around your frequency. And then you also have demodulated audio. So depending if it's a CW, you have a CW filter applied to it so that you can use it on a decoder that you have, or if it's an FM transmission or whatever else, like something which is sensible for the transmitter itself. And that brings the 2 things that are always happening on an observation. And then there is a third one which we're working actively right now, which is the demodulated data. So we have built on GNU Radio many different decoding flow graphs. Right now we're able to automatically decode APT transmissions, so image transmissions from NOAA satellites, FSK 9600, there is an AFSK 1200 coming up, there's a BPSK 4800, so things are starting to build up on that, so we can automate as much the decoding of that. If an encoder is not available, then you can, a decoder, sorry, is not available, then you can download the pass, the audio part of the pass, and process it locally and get the data that you need out of it. This is what an observation overhead looks like. Basically, we have more than 20,000 observations right now on network, and those are scheduled by people. So it says which satellite, in which station, by which observer, what's the status, regarding the returned data. Did it have any data on it or not? The frequency, the encoding, the time frame of the observation, and then some data about the pass itself. We're actually adding, I don't know if we already had that online on production, but we're adding also a polar graph there, so you can check the pass itself. And then when you go to the payload side of things, remember that we said 3 different things. So this is the waterfall itself. So you can see all the FSK 9600 bursts here that happened on this frequency. That's the waterfall. That's the audio. And you see a spectrum analysis of the audio here and waveform analysis here. And on the spectrum analysis, it's clear to see the data packets in here. And you can always download those or access it through the API. Sorry, one back. And this is the decoded data tab, so the third option that I was talking about. And because this one was a FSK 9600, then we actually got some raw bytes out of it. So all those are displayed, and you can download it and use it for further analysis. Any case, those end up in db.satnux.org, so they're available also from there, not necessarily from network.satnux.org. Now, talking about a bit about the local side of things, the client itself. The client is basically a Python instrumentation of various things that need to run locally in order for an observation to happen. It checks with network regularly about what is my job, what is my job, what is my job. So it fetches basically all the different things that are scheduled for it. And when the the time has come for the job to be executed, it commands the rotator, or if you don't have one, it doesn't. It starts the GNU radio script to collect the RF. It adjusts the frequency for Doppler correction. Then at the end of it, it generates the waterfall and the audio, and then uploads everything back to the network. It comes in, well, open source mode, so you can download the source code yourself and run it locally on your Linux PC, or you can have packages available for it. Or, and what really helped us, expanding the network lately, we also have a ready-to-flash Raspberry Pi 3 SD images. So you can download the Raspberry Pi image, flash it directly on an SD, and then boot your Raspberry Pi, and you should be good to go after a setup of basic parameters like your location and API key and things like that. What's important is also the latest point. Especially for people that want to keep using the ground station for other things, not necessarily having it tied to the network all the time. So the client comes in what we call two different modes. There's a network mode, which is what I just described. Basically, it takes command from the network, and that's how things work. But there is also a standalone mode, which you can select through the web interface of the client. And when you go on standalone, you can there is no connection to the network itself. You can schedule a pass for a specific, let's say an Oscar pass, and then you can use your own hardware or use the SDRs that are, if it's a TX-capable SDR, you can might as well use that, or use your actual hardware and then just let the client, command the Doppler shift and the rotator movement and everything else. And that's fine. We want people to be able to still use their ground stations when they're, when they want to. But at the same time, we want it to be easy to switch it back to the network. So once you're done with the standalone operation, you can switch it back to the network mode, and then the station becomes available for other people or yourself to schedule observations through the network and get people to have maximum usage of your station for tracking different satellites. How to get involved with SatNukes? We have many different ways. Well, the obvious one is set up a station. I know most of you have ground stations, so it would be really thrilling to see more ground stations in UK right now. We only have 2, and the one is under construction. So setting up a station, we have great documentation on the wiki for most of the things. Of course, it's an evolving project, so many things, moving around, but still there is there's a large community that can help you. We have the online forum, which is super active. We have an IRC channel, which is also active daily, and we can help you setting up a station. So feel free to reach out directly to me or to satnukes.org, or come and find me after if you want to set up a ground station. Other ways to get involved: contribute to db.satnukes.org. What I said before about gathering as much information as possible. If you're a code aficionado yourself, C, C++, Python, JS, we can use all different talents. We have a huge stack of different things, and we can always use more help. And of course, help with documentation and testing and automation. The final piece is something which is most times really missing from radio amateur type of projects. We try to stay as modernized as possible in terms of automation and continuous integration and continuous deployment of different code things that we do. And we've seen the results out of it, and they're really good. Being able for coders to code something new and really see it in production within a couple of hours on many different stations around the world, that really makes a difference in terms of the pace that the project is able to pick up. So we're really focusing on that right now. So for example, the Raspberry Pi 3 image builds, whenever there is a change on SatNuke's client or the GNU radio things that we're doing, there is a new build that is coming out. And also we're working on a solution right now to get automatically updates on Raspberry Pis themselves without, thankfully, breaking anything, which happens. So that was the SatNukes part of the talk. and I can now say that I'm a different kind of person and talk a bit about a different project of Libre Space Foundation, and that's UPSat. And UPSat is an open source software and hardware satellite that we had the opportunity to build. And it's out there right now, launched in space. So I'm going to be talking briefly about our journey through building an open source software and hardware satellite. So it all started many years ago when an FP7 program, QB50, I'm pretty sure most of you are familiar with it. The concept behind it is that von Karman Institute from Belgium wanted to do studies on the thermosphere, specifically about plasma concentrations and generations and the momentum and dynamics of plasma on the thermosphere. So they went out, they got funding on actually creating many different sensors, and they opened up applications for academic institutions to come in and create satellites using those sensors. So what you got is basically a discounted rate for a launch and the sensor itself. And then you had to build the whole satellite on your own. And initially the project was supposed to have like 50 different satellites. Of course, not everyone delivered on that. I think there were like 28 that actually got in space or on something around that. So that has been going on for years. I think they first started around 2009 or 10 was the initial kind of things. There were precursor flights, QB50P1 and QB50P2. QB51 also has a FunCube module on it. And the precursor flights actually informed a lot about the design of the QB50 satellites. So the way that we got involved in that was that one university in Greece, the University of Patras, was one of the 50 selected to create a satellite. And to their credit, instead of trying to just assemble a satellite from commercial and off-the-shelf boards that you can find out there, they said they're going to be building everything from scratch. And that's a tricky road to go down to, because first off, they haven't delivered a satellite before, and second, they weren't really sure how to go about it. So all sorts of risks amounted on that, plus there were huge budgetary constraints down the road for them. So they reached out to us initially just for the ground station itself, they wanted to have it on SatNuke. And then gradually we got part on all different projects, and what it ended up happening is that we took over the whole project, redesigned the satellite from scratch within 7 months, and delivered it as a complete thing from scratch. I think that the only thing that was left from their research is practically parts of the electrical power system and the structure itself. Everything else was kind of designed from scratch in this 7-month period. So this is the sensor itself. That's a multi-needle Lagamoir probe, and that sits on top of a 2U CubeSat. And those needles are basically able to detect the potential of plasma particles in wherever you are in that particular location in space. So that's the only thing that we started with. And then we ended up designing a whole satellite around it, right? So you can see here the sensor itself that's mounted on the thrust vector side of the satellite. So you imagine the satellite moving towards that direction. That direction down would be Earth, and you can see here a camera that we have on board in order to take some, simple pictures, because that's what you do when you get to space. You want to take some pictures and see how it looks like. And then all the different boards. I'm not going to go in, many details about that, mainly because you are mostly familiar about it, and there have been a couple of CubeSat presentations yesterday and today. But that's the electrical power system. That would be the attitude determination and control. We have active control of the satellite by magneto-torquers and spin torquer over here. Then we have the onboard computer, which is basically logging pretty much everything and running the experiment itself. And then the comms subsystem, which I'm going to go into details in a bit. A GPS module, the GPS antenna, and the antenna system itself. And that completes pretty much the mission and the satellite in terms of what's the different components. So it all started with this, literally. We just had, and that's January 2016. and we just had to print something like in a 3D printer to just start seeing what the satellite would look like. And imagine, like, at that point, January 2016, everyone said we were crazy because we had to deliver things in 5 months. And it ended up delivering in 7 months, and it was okay because the whole project, just got delayed any case. But starting to build a satellite from scratch with a 5 months, period ahead of you, like, no one really believed that we can actually make it happen. So we had to discover many things from scratch, including many of the safety procedures around their clean books and how to keep everything in the grade that they have to be. And then gradually, many different parts were coming to engineering model, like really things that we can work with, and starting to play around with them and start writing code for them. And things were moving like really fast. That's just a month after, or a month and a half after the previous picture that I just showed. So imagine you'd have 25 or almost 30 people working, full time and overtime and over the weekends just to do that. And gradually different pieces came into place. Because we designed the boards themselves from scratch, we had to account also for shipping and producing the boards and verification and going back to the drawing board in some cases, unfortunately, and revisiting many of the things that were along the way. But what was really critical in terms of success for this project was that the experience that we had from SatNuke and from our professional projects, like wherever we work, at least for the core engineers of Libre Space Foundation, is around Agile Development. And that was mainly on software. And of course, not everything translates from software to hardware, like especially when we come to Agile type of practices. But still, there are some best practices and learnings that you can apply on and try to have like a horizontal, engineering decision committee and like keep everyone in check, in place constantly, and really played around with a couple of different models, and we finalized kind of like the way that we're going to be working together within a month and a half or two. And then from that point onwards, it was just, like purely craziness of, creating, constructing, building, verifying, testing, coding, and everything else that comes between. This is the antenna system. I'm not going to say it again. Everything that you see here is designed as open source software and hardware from scratch. So that was not bought, obviously. Those are we didn't use tapes. That's a difference, mainly because we didn't have the space to do that. And what's happening here is that you can see this is a spooler, basically, and that's the downlink antenna that's on UHF, and that's the uplink antenna for VHF. And you can see that those two were like spooled around basically in this, what looks like a toilet kind of like cup. And then you would, once they're spooled, they're drawn back in, and then here you would have like a melting line, basically a dynema wrapped around the resistor that you would burn and like deploy the antennas. Spring here. And yeah, that's pretty much it in terms of the antenna system. You could see some matching here, components. That's the communications subsystem. So basically, we have two different things. Those two transceivers, those are Texas Instruments CC1120. And those were, this is the uplink one, and you wouldn't need any low noise amplifier or anything. They're pretty sensitive as it is themselves. And for the UHF downlink, we would have to put them through a power amplifier, sealed it enough, and then mount on the antenna. This is the MCU for the from the COM subsystem, and that's an STM32 from ST. And pretty much all the microcontrollers we used were STM32s. And you can see the progress from engineering models to FM flight-ready models, or almost flight-ready. And there's a lot of changes that happens in components and things, and like down to conformal coatings and everything else to bring everything in space ready condition. Yeah, this fit check for the satellite really early on. That's a Glovebox that we designed and created ourselves with 2 HEPA filters. That's an ISO 6 clean box in terms of the particles inside of it. And that's actually more than enough for building a satellite in there. And we didn't have access to that kind of equipment, so we had to actually build it ourselves. That's some early thermal testing. That's a PA burning the hell out of comms out there. That's an engineering stack and coding that happens in between. So we created pretty much 5 or 6 different engineering stacks that we can have them on all different teams and work concurrently, with each other. So everyone was flashing the other one's board, and they were trying to, really work in parallel around that. And for the command and control, we reused SatNukes too. So the SatNukes client, still actually until today, if you download it, it still has that's the web interface that I was talking about the standalone and the network mode on SatNukes. So if you switch on standalone mode, then on control, you have options for different satellites. Right now, only UPSat, but you could have also for other ones. And we implemented on JavaScript and then on Python, the backend, ECSS telemetry, telecommand, and telemetry protocol. It was a hard choice to do. Like most people actually go for a easier solution around this and not necessarily stick to ECSS standards, especially for like pretty basic commanding of your satellite. But we figured if we do that early, and thankfully we did, and it worked out, that we would have a reusable open source piece of code that other people can use on their CubeSats in order to do ECSS framing on both sides. So there is the GNU radio associated with it on the other side, and the Python instrumentation and everything else. And you can have like all the different parameters of ECSS framing tailored through that. So the command and control was built to the utmost standards basically, and it worked pretty well, even during the development itself. So that's some of the final pieces. That's an early assembly of the whole thing without the flight model components necessarily. And this is the flight models inside the clean box on the hackerspace. That's the vibrational testing. So you've seen that before. Everything went well in vibrational. So we didn't have to do anything, crazy on that. And then that's the thermal and vacuum testing. And we didn't have access to a thermal and vacuum tester, so we built one ourselves. So that's a vacuum chamber, and then you'd have like, bulbs producing heat, and then a giant fridge, like bringing everything down. And we could replicate, the oscillations of thermal conditions so that we can test the satellite on different conditions to pass basically all the specifications that we needed to, and compile the final readiness report and get acceptance in order to fly. That's the total mass loss measurement. Basically, once your satellite is done with the vacuum testing, you're measuring if there was a difference, of the outgases and how much, like in terms of percentage of your weight, that was. We were within specs, so that was good again. And finally, the EMC and EMI testing, the compatibility and interference testing. We didn't create an anechoic chamber, unfortunately. That's going to happen for the next project, by the way, and that's on the record now. But we were lucky enough to have a military standard EMC, EMI testing facility. There is you can literally fit a tank in here from the Greek military industrial complex. And then some field testing on that too. That's the power meter for field testing, and then transmissions and everything else. Those are the final delivery images just before we shipped everything to ISIS for. They were accepting basically all the different satellites and doing the final checkout tests. And this is us delivering the satellite, and that's a satellite literally like hours, like 20 hours before in the hackerspace with a final testing run of 24 hours testing. There was only one piece that was added during the checkout process, and that was a part of the sensor itself that had to be mounted, and then the satellite was ready to be integrated into the pods and then shipped out for launch. That's the integration that happened inside the pods, and you can see the satellite here, and then there's another one over there. That's a French one, again for QB50. The launch happened on the 17th of May this year. 17th of April. Yes, 17th of April. This year, and it went down on a Cygnus automatic transport module to ISS. And then from there, a month after that, on the 17th of May, the deployment happened. And UPSat is the first of those three that were deployed together. And soon after, actually 30 minutes after, there was the first beacon that we actually detected, and you can see other beacons in here. So there is a alternating transmission. So there's a CW beacon, and then 7 FSK 9600 baud packets, and then again a CW transmission. That's the beacon format of UPSat. And rightfully enough, like that happened through the SatNuke network. So we already had many different stations around the world, and we scheduled UPSat with the early telemetry, with the early Keplerian elements that we can find. Basically, you're using the ISS elements for that initially on the deployment, and then we're just waiting for the waterfalls, to come back and see whether we actually worked or not. And we did, and we're super happy about it, and we still do from time to time because there are some power issues with power generation. But it's still operational, so we're pretty happy about it. So what's next for us after UPSat? So we sat down and we communicated as much as possible about UPSat and tried to bring more people into open source and really avoid reinventing the wheel each time we're creating a satellite. And this is happening to that much extent, which is like really frustrating for all of us. We try to reach out to many different organizations that are creating payloads or whole CubeSats that might be willing to actually open source them, and we got a pretty good response around that. So we decided to create an open source CubeSat workshop together with the LibreCube people from the ESA Operations Center in Darmstadt. So that's going to happen on the 23rd and 24th of November. There was a call for abstracts that went out, and it's over now, unfortunately. But you can still participate in the workshop. There's going to be, like, literally, we want it to be a real workshop, so not just lectures of people, like, talking about the project and then leaving the room. But we have crafted in, like, 50% of the time, basically roundtables and working sessions so that we can discuss about collaborations and efforts around it. So, yeah, that's what's next for us. And trying to find the next project and expanding the SatNuke network as much as possible. Thanks a lot.